In the last lecture, we discussed frequencies of photons and wavelengths of photons emitted by hydrogen atom. We also found that if the transition takes place to the ground state, then the series formed is called Lyman series, and if the transitions are up to the state n equal to 2, then they are known as Balmer series. And we also learnt that these series, Lyman, Balmer or other series, can also exist in absorption spectrum. That is, out of continuous spectrum, lines of this energy they can be abstracted, so that you get in that radiation spectrum, in that you get dark lines. These are lines of absorption. This is called absorption spectrum. This we did in the last lecture. Then we introduced the idea of quantum as proposed by Planck to explain the black body radiation. We also found that the electrons, the free electrons existing in a metal piece, if they have to come out, they need a certain minimum energy, and that energy is called the work function of metals. This energy can be given in various ways. One of the ways is to heat a piece of metal, so that electrons get sufficient energy to come out. This is known as thermionic emission. This we all discussed in the last lecture, and now we continue from that point onwards. We also said that the energy can be given to free electrons in the form of an electrostatic field, force exerted by the electrostatic field. If this is a piece of metal and we place this piece of metal in a very strong electrostatic field, then the free electrons in this piece, they experience the force of this field, they gain energy and they can come out. This is known as field emission. Normally we need very strong fields, but these days special materials have been developed, so that we, even if we have a field exerted by a 12-volt battery, applied by a 12-volt battery, even then it can extract electrons. What is this arrangement? Let us see. A field effect display for high definition pictures, the kind of pictures that you get on an LED TV at your home. How does it work? We have millions of these CNT cathodes. CNT stands for carbon nanotubes. Nano, is 10 to the power -9 meters. So, these are very thin carbon pieces and carbon tubes, and if you apply a field even of 12 volts, electrons can be emitted. So, we have millions of these carbon nanotubes which form a cathode, and then we apply the field and the electrons come out and they strike phosphors on the viewing screen. Phosphors are substances which give light when they are hit by electrons, and the phosphors can give lights of different colors. Here the blue, green and red, and it is a combination of these colors which forms the picture on the picture tube. So, this arrangement, in earlier televisions we had transformers which give very high voltage for the picture tube, but now this field effect display works only at 12 volts because of these carbon nanotubes, and this kind of arrangement is used now in high definition televisions. The third way in which electrons can be given energy so that they come out of the piece of metal is known as the photoelectric effect. In this case, we make photons incident on this piece of metal, and these photons give energy to these free electrons, and they, if the energy is sufficient, they come out. These are the ejected electrons. These are known as the photoelectrons. So, we shine this piece of metal with photons, and if the energy in the photons is sufficient, then these electrons get that energy and they can come out as photoelectrons, and this effect is known as photoelectric effect. The discovery of photoelectric effect and its analysis by Einstein suggested that the light in this case, light waves in this case are behaving like particles, and this came to be known, these particles came to be known as photons. We have been using word photons, but actually it was after this that they came to be known as photons. Since photons have energy equal to h nu, where nu is an attribute of a wave, you see nu is the property of a wave, frequency is the property of a wave, and energy is discrete. So, it is the property of a particle, and so there is duality. We shall study below the argument which led to this development. So, in photoelectric effect, a metal cathode emits electrons when photons are incident on it. This is a formal definition of photoelectric effect. The experimental setup to observe the photoelectric effect is very simple. We have a cathode, a piece of metal, on which we bombard the electromagnetic waves or photons. If the energy in these waves is sufficient, in these photons is sufficient, then electrons are emitted by the cathode and they are captured by the anode. Anode has a positive potential, so these electrons are captured by the anode. To find out the potential difference between this and this, cathode and anode, we have a voltmeter, and to find the current that is going through the circuit because of the photoelectrons, we have an ammeter. So, that is a setup, a very simple setup for the experimental observations of the photoelectric effect. And there is arrangement to vary the intensity of the photons. Intensity, you remember, is the number of photons going through a cross section, unit cross section per second. So, the intensity, that means the number of photons which go through a given cross section varies, increases or decreases. So, there is arrangement for varying the intensity of the source here. There is also arrangement for changing the frequency, varying the frequency of the photons emitted by this source, and there is also arrangement for varying the potential difference between the cathode and the anode. All these things we shall study. Effect of intensity of photons. Intensity is actually, as I have said just now, is the number of photons. So, if we by intensity, if we increase the intensity, the number of photons increase. If we decrease the intensity, the number of photons decrease. So, what happens if we change the intensity of photons? If the initially, if suppose we start the experiment and this does not show any current, this ammeter does not show any current, then we increase the frequency of this source, frequency of the photons or the energy of the photons initially. Once the current is registered by the ammeter, then we stop changing the frequency, then we vary the intensity of the photons. And if we do that, then we find that the photoelectric current varies as in direct proportion to the intensity of photons, but that is if the frequency is sufficient to eject the electrons. Once that frequency is crossed, then the photoelectric current is proportional to the intensity of photons, or we may say the current is proportional to the number of photons. So long as the frequency of the incident photon is higher than a certain frequency, this frequency is called threshold frequency. Below this frequency, there is no emission of photons. Above this frequency, there is emission of photons, and therefore, this is known as threshold frequency. So, another thing that you need to know is this, that as soon as the frequency is equal to threshold frequency or higher than threshold frequency, as soon as the photons are incident on the cathode, immediately without any lapse of time, we have the current. That means, electrons are emitted as soon as the photons are incident. There is no lag, there is no time difference between the photons being incident and the emission of electrons. There is no time lag, and this is a very important. We shall see that this argument was used by Einstein to show that waves are behaving like particles. Now, let us do the second part. Let us change the anode potential. Let me show you the circuit again. So, we are varying the anode potential. We are changing the potential given to the anode. What would this mean? This means the capacity of the anode to attract the electrons would vary, and that is what we want to do. So, effect of anode potential. Keeping the frequency of photons fixed, that means when we say fixed means above the threshold frequency. If the anode potential is gradually reduced, then what happens? If the anode potential is reduced, then there is a slow decrease in the current. That means, the number of electrons being captured by the anode is decreasing. Why is it decreasing? Because there is no sufficient attraction between the electron and the anode. So, that if electrons do not have sufficient kinetic energy, they would not reach the anode. If they have sufficient energy, then they would reach the anode. But if you reduce the potential further, then this kinetic energy electrons will not reach the anode. Higher energy photoelectrons will reach the anode. If you keep on doing this, keep on reducing the potential of the anode, then you reach a point minus V0, where the current stops. This means that V0 determines the highest kinetic energy that is given to the photoelectron, because at this stage even the highest energy photoelectron is not being able to reach the anode. So, therefore, this is a measure of the highest kinetic energy given to the photoelectrons, and this is known as cutoff potential. Why cutoff? Because the current in the ammeter is cut off, current in the circuit is cut off. This is known as cutoff potential. Now, if we keep everything the same now, once we have found the cutoff potential, frequency we do not change, but change the intensity, what would happen? When we change the intensity, then the number of photons goes up, and therefore, more or higher current is recorded. So, the intensity is responsible for increasing the current. The shape of the graph remains the same, the cutoff potential remains the same, because cutoff potential is a function of the frequency and the work function of the metal. Frequency we are not changing, we are changing only the intensity. So, frequency is constant, therefore, V0 is constant, intensity we are changing, and when intensity increases, that means more or higher number of photoelectrons is available for the anode to capture, and therefore, the current becomes high. And you can also see that the current becomes, there is a maximum, it achieves the saturation current. That means, for example, at this anode potential, all electrons emitted by the cathode are captured. So, therefore, there is a saturation current cannot be higher than this. So, V0, as I said, is called the cutoff potential or stopping potential, it is sometimes called stopping potentials. When the anode potential is made negative, fewer electrons are able to reach the anode. These are those electrons which have sufficient kinetic energy to overcome the repulsion between the electrons and the anode. The existence of cutoff potential implies that electrons with even the highest kinetic energy are not able to reach the anode, as I said earlier. V0 is thus a measure of the highest kinetic energy with which the electrons are emitted. In other words, we can write the maximum kinetic energy half m e V max squared is equal to E V0, where V0 is the cutoff potential. Now, let us look at the effect of frequency. Let us look at the same diagram again. Now, intensity is constant and we are now going to change the frequency. Of course, it will be higher than the threshold, but we are going to vary it, but it remains always higher than the threshold, because below threshold frequency you do not have any current. So, when we change frequency, we find that we are again plotting photoelectric current against anode potential, and we are changing the frequency. You see what is happening? There is a saturation current, and as we decrease the anode potential, then we have these three cutoff potentials, and for nu 1 less than nu 2 less than nu 3. The cutoff potential, as I told you, is a function of frequency and of course, the metal. If the metal is constant, then it is a function of frequency. So, higher the frequency, higher is the cutoff potential. Lower the frequency, lower the cutoff potential, because higher energy, higher frequency gives higher energy to the electrons. Therefore, they come out with greater kinetic energy and are able to reach the anode. Let us now study the effect of frequency on stopping potential. Then now, if we plot stopping potential against frequency, we find that at frequency nu 0, below that frequency there is no current. Whatever the stopping potential, there is no current. This means this is the minimum, this is the threshold frequency, and this gives just sufficient energy for the electrons to come out to the surface and not be able to go to the anode. If the frequency increases from this point onwards, then of course, it also gives kinetic energy to the photoelectrons and they can reach the anode. So, that is the relationship between V 0 and nu. So, as long as nu is less than nu 0, no photoelectrons are emitted. If nu is greater than nu 0, then photoelectrons are emitted. If we plot the same graph for various metals, we find curves like this, and this is actually procedure for finding the work functions of the various metals. Metal 1, for example, has the threshold frequency nu 0 1, therefore, its work function is equal to h nu 0 1. Metal 2, the threshold frequency is nu 0 2, therefore, the work function is h nu 0 2 and so on. So, if we want to find out the work function, we plot V 0 against nu, and wherever there is a cutoff on the nu axis, we get the work function for that metal. If we have such a line, we can easily write the equation y equal to m x plus c, the linear function. We can write the equation, and this equation has this form: E V 0, the energy here is equal to h nu 0, nu minus nu 0, because this difference of frequency into h is the energy which provides kinetic energy to the photoelectrons. Therefore, we can write E nu 0 equal to h nu minus nu 0, h nu minus h nu 0, or h outside in the bracket nu minus nu 0. Since h nu 0 is equal to the work function, as I have been saying, this is h nu 0 1 is the work function of this metal, h nu 0 2 is the function for metal 2, and so on. So, since h nu 0 is equal to the work function phi, this equation can be written as h nu equal to the work function goes on the other side, and this is a measure of the kinetic energy. You remember that stopping potential measures the maximum kinetic energy of the photoelectrons. Therefore, we write this equation as h nu equal to kinetic energy plus the work function, or the kinetic energy that the electrons get is equal to the energy of the photon minus the work function. That is, the photon energy provides energy to the electron to overcome work function and acquire kinetic energy, so that the electron is able to reach the anode. And it was the derivation of this equation that fetched Einstein the Nobel Prize. How he derived this equation we shall see in a moment, but this kind of arrangement, this is used for finding the Planck constant, because the slope of this curve is h by E. E is known. So, if you can find the slope, you can find h. So, it is one of the methods by which the Planck constant can be determined in the laboratory. So, since this was a very important equation which won Einstein the Nobel Prize, let us see how he arrived at this equation. And as I have been saying earlier, he arrived using the idea of particle nature of light, and surprising, this was the time when wave theory of light was accepted by everybody. At that time, Einstein was bold enough to say no, photons are actually bundles of energy h nu. This wave nature of light is not able to explain photoelectric effect. So, to arrive at this equation, let us collect the key observations of these experiments, all the experiments that we have done. Let us collect the key observations. 1, if the frequency of photons is below the threshold frequency, there is no emission of electrons. Whatever the intensity of radiation, that is important, that if the threshold frequency is the frequency of photons is less than the threshold frequency for a particular metal, then whatever the intensity, that means whatever the number of photons, it does not matter, no photoelectron is emitted. There is no time lag. I pointed out to you during our discussion that there is no time lag. As soon as the photons hit the cathode, immediately the electrons are emitted. There is no time lag. That means, as if the energy is being transferred instantly. The kinetic energy of electrons is proportional to the frequency of photons as long as nu is greater than nu 0. And lastly, the cutoff potential is determined by the frequency. The cutoff potential is determined by the frequency. You remember that curve where we varied the frequency. The cutoff potential is determined by the frequency, and as long as the frequency is constant, the intensity of photons merely affects the saturation current or the number of electrons emitted. It does not affect V 0. So, the intensity does not affect V 0, frequency determines V 0. And the kinetic energy of emitted electrons depends only on the energy of the photons and not their intensity. It is clear from here and other experiments also. So, all these key observations can be explained by just one hypothesis, and that is called the quantum hypothesis, which implies that, what is the hypothesis? In this phenomenon, that is in the photoelectron emission, the electromagnetic waves behave like particles. Each particle or photon of frequency nu carrying energy quantum h nu. So, if we make one hypothesis, you will recall that actually this is what Planck also said, that radiation consists of the discrete energy quanta. So, Einstein made use of this discrete energy quanta. Why can't the classical theory not explain it? Why can't the wave theory cannot explain photoelectric effect? Let us see. You see, you have waves. The waves keep on striking on the cathode, and they deposit energy on the cathode. And once the electrons get sufficient energy, then they can come out. But there will be a gap between the photons being incident and the photoelectrons coming out. This gap is not there. That means, waves cannot explain the photoelectric emission. 1. Second, so over time even low frequency waves should be able to deliver enough energy to dislodge electrons from the metal, but we have seen that low energy waves cannot emit electrons. However, there would be a time lag between the waves striking the cathode and the emission of electrons. This is contrary to observations. You see, the waves depositing energy slowly and then electrons coming out, this is not observed, and therefore, this is contrary to observations where the frequency has to be above a certain minimum. There is a threshold frequency and the frequency has to be above this minimum threshold frequency, and then there is no time lag. As soon as the waves hit the cathode, the photoelectrons come out. On quantum hypothesis advanced by Einstein, let us see the explanation. The photons associated with the wave has an instantaneous impact on the cathode like a billiard ball. I mean, as soon as it strikes the surface, it delivers energy, not that the wave keeps on striking the surface and then energy is delivered. No, the wave acts like a billiard ball. The particle attached to the wave or the particle nature of wave is such that it acts like a billiard ball. As soon as it hits the surface, it delivers sufficient energy and electron comes out. Moreover, the higher the number of photons, higher the number of these photons, higher is the photoelectric current. But again, there must be a minimum frequency. If we have minimum frequency, then electrons will come out immediately, and now if we increase the intensity, the number of photons increases because the number of photoelectrons increases because there are large number of photons now hitting the surface. So, on quantum hypothesis, just one step and everything concerned with the photoelectric effect is explained, but not with the waves. So, that was the departure that Einstein made. He said in this process photoelectron emission, the electromagnetic waves behave like particles, each photon carrying energy h nu. And lastly, the kinetic energy acquired by an electron will be difference between the energy of the photon and the work function. So, you can write kinetic energy equal to h nu minus phi. H nu is the energy of the photon, phi is the energy needed for the electron to come to the surface, and therefore, the difference goes into the kinetic energy of the photoelectrons. And as long as nu is greater than nu 0, the photons are emitted, photoelectrons are emitted. As long as nu 0 nu is less than nu 0, the photoelectrons will not be emitted. The emission would be immediate, and the kinetic energy would be the difference between the photon energy and the work function. So, all these things were explained by just one hypothesis by Einstein. In the next lecture, we shall extend this argument that here the waves are acting like particles. Now, we shall see that particles can also act like waves. This was de Broglie hypothesis, and we shall see how the two are related, the wave of the frequency and the momentum of the particle, how they are related. And we shall also see the waves accompanying particles.